Hello there, and welcome to Chapter 9 of our lecture series here. Chapter 9 is all about stoichiometry. It's going to be another longer chapter, so this lecture will be broken into two parts. This is going to be part 1, basic stoichiometry. Shall we begin? I think so. Okay, welcome here, Chapter 9, up on tap for today. Calculations from chemical equations. So in this chapter, we're actually going to put together several topics from previous chapters where we talked about balancing equations, where we talked about grams to moles, molar mass, and converting to moles. We're going to actually put those together and use equations to figure out, for example, how much product we may make, how much reactants we started with. So let's get into it. And one of the most important sort of principles in this chapter is what we kind of saw, I think, in a previous chapter, this slide, just to remind you, one of the important things for sure is the idea that we need a balanced equation. So remember that always when we have an equation, regardless if it's sort of given to you, balanced or not balanced, you should always make sure that it's balanced. So again, if you see coefficients, probably a good shot that it's going to be a balanced equation. You probably should still kind of take a moment and check it. If you don't see any coefficients in the equation, you should definitely check it hard and make sure that it is balanced, and take a hard look at it and make sure that it is balanced, or if it's not, that you do balance it. So when we do have a balanced equation, there's certain relationships that we could actually get from the equation, which is really important, and especially what we're going to talk about in this chapter, which is really what is referred to as stoichiometry. And one of the ways that we will use sort of the relationship that we see from the balanced equation is based off of these coefficients. So here we have a 2. Remember that if there is nothing written here, again, that represents a 1. Here we do have a 2. We could say that this is 2 molecules of H2 react with 1 molecule of O2 to form 2 molecules of H2O. We could also look at the bottom here, which is our conservation of mass. So because we don't lose any elements along the way in a chemical reaction, again, the only thing that happens is electrons and bonds being broken. We don't touch the nucleus, as we talked about a number of times, I think, up to this point. And because we don't touch the nucleus, we don't touch protons in a normal chemical reaction. We have the same elements that we start with and that we end with. They're just in different arrangements in terms of compounds and substances. So we have that conservation of mass. So again, in this case, we have the same number of hydrogens on each side of the arrow, also the same number of oxygens on each side of the arrow. So thus we would have the same mass of each of those elements on each side. Since hydrogen, again, on the left is 1 gram and 1 gram on the right, and oxygen 16 grams on the left and 16 on the right. Now, when we talk about stoichiometry, which is pretty much the entire focus of this chapter, the important relationships that we use from equations is really this relationship here. And once again, this is what is sometimes referred to as the mole to mole relationship. And again, it's a really important thing here. Sometimes people get really confused about, sort of how we get the relationship. It is nothing more than the coefficients, again, in the balanced equation is where we get this kind of mole to mole relationship. And we could say that for every 2 moles of H2 that we put in there, it will react with 1 mole of O2 and it will form 2 moles of H2O. So that is pretty much the relationship that we're going to use strictly here when we do stoichiometry problems. And again, as we can see here, comes from the balanced equation, which is why always the first thing that you do is make sure that that equation is balanced. So let's take a look at really stoichiometry and sort of questions that we oftentimes are looking to answer when we do these type of problems. So we will sometimes want to know, if we start with a certain amount of reactants in a product or in a reaction, how much product would we produce? We also sometimes want to know, like, okay, we produce this much product. How much reactants did we want to start with? We could also, and a very important sort of stoichiometry relationship is we could actually stay on the same side of the arrow. So what do I mean by that? So obviously here we have reactants, we have products. So when we do stoichiometry problems, we can, if we kind of know, how much reactant, we can figure out, how much products we would produce. We also, if we know, as I just mentioned, how much products we produced, we can figure out how much reactants that we started with. We could also, for example, if we had, say, an equation like this, the very creative A plus B goes to C plus D. If we had an equation like this, we could also use stoichiometry, for example, to figure out things like, if I have this much of this reactant, how much of the other reactant will I need? And vice versa. We could kind of do it between reactants. We actually don't, in stoichiometry problems, have to sort of do the relationship across the arrow. We could stay on the reactant side. The same thing with our products. If we're able to figure out, for example, how much of our product here, say C, that we produced, we could do some stoichiometry calculation and figure out how much D we would actually be making, and vice versa. If we know how much D we made, we could actually go back and figure out how much of the other product that's there. So sometimes when people do stoichiometry problems, they have a misconception that you always have to sort of do the relationship sort of across the arrow from reactants to products or products to reactants. And you do not need to do that. You can actually do it for everybody in the equation. You could do it between two reactants. You could do it between two products. You could do it between a reactant to a product. You could do it from a product back to a reactant. So it's very useful calculation. It's a really important calculation in chemistry. And it allows you pretty much, if you know one sort of piece of information, to figure out pretty much what's happening with everybody else in that sort of equation or reaction that's taking place. So the units that we deal with in stoichiometry could really be a lot of units, moles and grams. Later on, like for example, in solutions, we could use liters and molarity sometimes. And also for gases as well, we can use liters. So for this chapter, though, we probably, and in a lot of stoichiometry problems, we will use sort of these guys as our units. And also a really important reminder, that is grams to moles, or moles back to grams. And remember that it is the molar mass, right, that we get from the periodic table. That's our conversion factor to do that. So we do use the molar mass a lot in stoichiometry problems. And again, that's our grams per mole. And once again, we get that from our periodic table. So again, we're going to really tie together a lot of some previous chapters, definitely the balancing equation, writing equations, and also doing the grams to moles, moles to grams sort of calculation. It's very prevalent in stoichiometry problems. So the approach that we use was referred to as the mole method. It uses that mole to mole relationship that you find from the balanced equation to figure out really what you're looking for in terms of your calculation. And it's based solely on the stoichiometric coefficients from the balanced equation. So there's really no sort of calculation you have to do to figure out the stoichiometry relationship or the mole-to-mole relationship once you have the equation balanced. So once it's balanced, you're in a good shape to sort of start the problem. So let's talk about the normal sort of steps along the way to do stoichiometry problems. There's actually 5 listed here, but in a lot of cases, we will kind of do 4 basic steps. But let's talk about each of these steps here. The first thing you want to do is make sure that you write the correct formulas for the reactants and the products. So I would say maybe 90% of the time, 95% of the time, you might not need to do step 1 here because you probably will be given the actual chemical equation. This would be a case where you're not given the chemical equation. Maybe you're just given the reactants. Maybe you're given things in words. So as we talked about when we talked about that chapter about balancing equation and writing equations, you want to make sure that you get all the proper equations first, and then you want to balance the equation. So if you have to sort of start from square one, step 1, all you have is words, all you have maybe is a couple of reactants, make sure that you complete the reaction or equation correctly with the proper formulas. And then, as we talked about many times, then it is off to balancing the equation. Pretty much none of this calculation will work correctly if you do not balance that equation. So you got to make sure that the equation is always balanced. Once again, if you're given the equation and there's no coefficients there, or there are coefficients written, you should take a moment and double check that it is balanced. And again, if it is not balanced, make sure that you do balance it. Next thing you want to do is convert whatever they give you basically into moles. So this is a normal step. A lot of times you're going to get it into grams, and then you're going to get it into moles. And as we just talked about, that's going to be your molar mass from the periodic table that you're going to use to do that. Now, getting it into grams and then to moles, you may be in some other units. Maybe you're in pounds, maybe you're in kilograms, maybe you're in something else. So you may be a couple of steps to get it to grams, but once you get it to grams, you then want to take it to moles. So a lot of times it is kind of given to you in grams, and then you kind of take it from grams to moles, but it is possible it could be given to you in some other unit that you first need to convert to grams and then go to moles. The reason you really need to do that is the next step, which is really the big stoichiometry step. You're going to go to that balanced equation and you're going to find that mole to mole relationship. And again, those are the coefficients from the balanced equation. And that is really why in the step before, we need to get it into moles so that everything cancels out correctly when we get to the stoichiometry. Once you do that, you just did the big stoichiometry move, and you will be always at this point in units of moles. And the last thing you want to do is convert that to some other unit. This again could be a situation where maybe you are, I'll write it over here because I think I just wrote on my face, moles to some other unit here. You oftentimes at this point in the problem, you also will kind of take it moles back to grams a lot of times. So once again, the molar mass here from the periodic table is oftentimes used. So when we do basic stoichiometry problems, which is sort of what we're going to start with here today, there's really kind of 4 steps. So most of the time, if you follow these 4 steps, which is make sure you have a balanced equation, convert to moles, make sure you find the mole to mole relationship. And again, that is from the balanced equation. And then you want to take moles to some other unit. So these are really for pretty much every basic stoichiometry problem that you have. This is basically the 4 steps that you want to follow. Now, what happens if something is done before for you? You actually just go forward. So you do not want to go you do not want to go backwards. So sometimes what happens is something is done for you. So for example, let's just say instead of being given grams, you're given moles to start with. So sometimes people go, they kind of unconvert it to moles, back to grams, and go back to moles. So don't go backwards, just go forwards. If it's already in moles, then all you have to do is go to the next step, step 3, and then go to step 4. So if something is done for you, you just kind of go forward, don't go backwards. But pretty much in basic stoichiometry problems, if you follow these 4 steps, it should lead you to the right answer. So let's take a look at an equation here, and this equation is balanced, and that's one of the first thing that we do want to look at here. And we can see that we have 2 carbons on each side. We also have 4 oxygens on each side. Once again, there are 2 here, another 2 there is 4, and again, 2 times 2 is 4. So from this one equation, we actually can come up with several relationships or stoichiometric relationships that we can use in a problem. So for example, here, we could say that for every 2 moles of CO that I put in there, and again, that's coming right there from the coefficient, I would have to put in there 1 mole of O2. I could also say for every 2 moles of CO that I put in there, I would need to produce 2 moles of CO2. I could also say for every 1 mole of O2, I will produce 2 moles of CO2. These are 3 equalities. And these are equalities, just like we were talking about when we were talking about conversion factors and dimensional analysis. They are equal to each other. They are stoichiometrically equal to each other. And you may be saying to yourself, 2 doesn't equal 1 or 1 doesn't equal 2. And that is true. It's not equal to each other in terms of numbers, but they're stoichiometrically equal to each other in terms of like proportion, if you will. Like in order for this reaction to happen, you got to throw 2 moles of CO with 1 mole of O2. Like if you're baking cookies, for example, you got to throw so much flour, so much sugar, so much butter in there to get like a 2 dozen cookies to come out, or a dozen cookies, depending how big you make them. It's kind of the same idea here. So although they're not numerically equal to each other, they are equal to each other in terms of a relationship of how this reaction has to take place. So because they are technically equal to each other like equalities, we actually, just like conversions, can actually write 2 conversion factors for each of these equalities. So for example, here we can say for every 2 moles of CO that I put in there, I could get 1 mole of O2 that also gets put in there. I could also say for every 1 mole of O2, I have 2 moles of CO. And again, that comes from obviously this guy. I could write conversion factors for my others. So if I were to do this one here, I could say for every 2 moles of CO, I get 2 moles of CO2. Or for every 2 moles of CO2, I get 2 moles of CO. For the last one there, I can write my 2 conversion factors. Every 1 mole of O2, I get me 2 moles there of CO2. Or for 2 moles of CO2, I get 1 mole of O2. So as you can see from this one balanced equation, we could actually come up with 3 equalities, 3 of these mole to mole relationships. We also will actually come up with 6 conversion factors that we could get from this actual equation. And honestly, that is really what stoichiometry is. It's really just conversion factors. So here's the deal. In a stoichiometry problem, you're given information about somebody in the equation that you're really not interested in. You're maybe interested in somebody else in the equation. And you need a way to convert from that information that was given to you. For example, here, say I was given information about CO in this equation, but I want to know how much CO2 I would produce. I need a way to go from CO to CO2. So instead of looking up in a table where you will not find anything like that, the relationship between CO and CO2 to find a conversion factor, we actually use the equation itself as the conversion factor. And that would allow me to do that. So will you use all 6 of these conversion factors in a problem? The answer is no. Most likely you'll just pick the one that you need. So probably one of these would work for a situation that we're looking for. So how does this all work? Let's take a look here. So let's just say, for example, up and over. Let's just say in this one here, we had, let's say we produced 15.5 grams of CO2. And we wanted to know how many grams of O2 did we start with. So if we were to do this type of problem, this little example here, we've already established all of our sort of conversion factors and mole-to-mole relationships that we could get from the equation. So we want to also think about those 4 steps that we talked about. And those 4 steps, again, let's just erase a little bit of this here, just get a little bit more room. Remember that core basic step for stoichiometry is we want a balanced equation. We want to convert to moles. We want to do I guess that would be 3. This is our mole to mole relationship. And lastly, convert moles to some other unit. So let's just kind of go through this list right here with this problem. Well, I need a balanced equation. So step number 1 is done. So that is all good. Now, the next thing that I want to do is convert whatever they gave me to moles. So in this particular problem, I am given 15.5 grams of CO2, and I need to take it to moles. So to do that, I would need the molar mass of CO2. So once again, to do that, we will go to the periodic table. Carbon is 12.01 grams per mole, and oxygen is 16, and there are 2 of them. And again, we're getting these numbers from the periodic table below the element. And we're going to take 12.01 plus 32, basically. It's going to give us 44.01 grams per mole. So we are going to use that molar mass as our conversion factor to convert our grams that they gave us into moles. So we'll do that. We'll take 15.5 grams of CO2. Using our molar mass, remember opposites cancel, so we do need the grams on the bottom here. Grams will cancel. And that's going to give me 15.5 divided by 44.01. It's going to give me something like 0.3522 moles of CO2. So this is the second step that I need to do, which was convert to moles. Now, at this point, I am still really over here. All I really did was convert the units from grams of CO2 to moles of CO2. And that's good, but ultimately I'm looking for O2. So I need a way to go from CO2 to O2. And this is where the stoichiometry comes into play. So if I look at the equation, I could see that for every 2 moles of CO2, I have 1 mole of O2. And that was the relationship that we had here. And that gave us really these 2 conversion factors that we could use. And again, we're not going to use them both. We're going to use whichever one's going to get us to O2 in this case. So the third step is actually the big stoichiometry move that we want to do. And the big stoichiometry move here is we're going to take our number that we just got, 0.3522 mole CO2. Remember, now we want to get rid of CO2 and we want to end up at O2. So the conversion factor that's going to do that is actually the conversion factor here on the left. Remember, again, opposites cancel. So here we will do that. And from the balance equation, and this is the stoichiometry part, 2 moles of CO2, which once again is nothing more than just a coefficient, gives us 1 mole of O2. So again, if you blink your eyes, that's the big stoichiometry part right there. That conversion factor that we get from the equation. That's going to get rid of the moles of CO2. We will now be in moles of O2. And if we divide that by 2, we're looking at 0.1761 moles of O2. Now, if by some chance you wanted the answer in moles, you would be done. You could just put a box around it and you would be fine. But in our case, we actually want to go to grams. So in this case, we do need to do step 4, which is you should always be in moles at this point. If you did everything correctly, So because you're in moles, we now in this case want to go back to grams. So once again, that is the molar mass is going to be our conversion factor to do that. Also a reminder though, and sometimes people get confused at this point, we need to make sure that we're using the proper molar mass. We are no longer at CO2. We are at O2, right? So we do again need to, for step 4, go back to the periodic table and figure out the molar mass of just O2 in this example. And that is 2 times 16. And again, that comes from the periodic table. And that's going to give us 32 grams per mole. That's going to be our final sort of step here. So I'll just call it step 4 right there. And we're going to use the molar mass. We're going to put the grams up on top in this case, 32 grams of CO2 per mole of CO2. Moles cancel, and I'm just going to go here so I don't write on my face, I think, times 32. That's going to give us here 5.64 grams of CO2. Now, in terms of significant figures, really the only number in this problem was this one, which was 3 significant figures, and that's really where we should end up. When I got an answer here and I got an answer here, I did take it to perhaps a couple extra digits. And to be truthfully honest with you, when I was doing the calculation, I left the entire number in my calculator and just continued on with the calculation. This gives us 5.64 grams of CO2. So what does this number really mean? It means what we just figured out was if I were to produce here 15.5 grams of CO2, I would have had to put into that equation or that reaction 5.64 grams of O2. And if I did that, I should produce 15.5 grams of CO2 based on the reaction. Now, as you can see here, these are the 4 steps that you want to follow in a basic stoichiometry problem. Can you do it all in one calculation? You absolutely can. You can do it all in one calculation. And what I mean by that is you really could just do one calculation that takes you from here to here and from here to there, and then obviously to our answer without getting kind of the answers in between. I would say that if you do get answers in between, which is a perfectly okay way to do it, just make sure you don't round too much until the end. So like I did in my calculation, I would keep the entire number in my calculator and continue on with the calculation. Or if you are going to round, take it to a few extra digits, and that way you won't get any rounding errors when you do it. So these are the 4 steps. Conversion factor basically from the balance equation, really important here. So let's take a look at one here, and why don't you give it a try. Lithium metal reacts with water to form hydrogen gas and lithium hydroxide. How many moles of hydrogen can be formed by the complete reaction of 5.32 moles of lithium with water? All right, so give it a go. Let's take a few moments here. I don't see an equation, so probably a good place to start. Remember the 4 basic steps here. Balanced equation. Grams to moles. Relationship. And moles is some other unit. All right, so follow those steps, give it a go, and then we'll talk about it here together in just a second. Okay, so let's take a look here and see how you're doing. So in this case, we do not have an equation. So we do want to make sure we get a balanced equation. So this would be the example where we're talking about there when we're going through the steps that we actually have everything in words. We actually don't have an equation given to us. So we want to make sure we first start with the right formulas. Lithium metal is just lithium by itself, so that's Li. Reacts with water, which is a little H2O action. That's going to form, which is the arrow, hydrogen gas. Remember hydrogen gas, oxygen gas, nitrogen gas, chlorine, fluorine, and so forth. Those are diatomic molecules, so H2 is the proper formula there. And lithium hydroxide. So lithium is +1, hydroxide is -1, so we get a little LiOH action at this point. Now that we have the unbalanced equation, remember that none of the stoichiometry part works if you do not have a balanced equation. So we need to do a little balancing. So let's see here off the top of my head. Maybe like a 2, and maybe a 2, and maybe a 2. I feel like I'm just putting 2s down. How did I do that? I'm going to stop putting 2s at this point. 2 lithiums on each side, 4 hydrogens, so 2 and 2 over here on the right, and 2 oxygens. So it looks like we are now balanced. So now we could really officially check off the first step. Second step is take whatever they gave you and convert them to moles, basically. So we want to end up in moles after the second step. Really, the only thing that's given to us is we are starting with 5.32 moles of lithium. So that's already in moles. So this step is done for us in this case. So this is, again, a situation where you don't want to unconvert it, reconvert it, or anything weird like that. It's already done. You already have the moles of lithium here, so no need to, go back to step 1. That means we just go forward here. So step number 3 is the mole-to-mole relationship. So we're looking for 2 things that we're interested in. One thing that we are interested in is whatever they gave us. So clearly they gave us this with our lithium. The other thing that we're interested in is what we're trying to find, which is water in this case, right? No, we are not. We're trying to find hydrogen, which is this guy right there. There we go. Also good to read the problem correctly. I guess that helps. Try to steal that out of there. That took too much. 2 back there. So that is the 2 guys that we're interested in, lithium and H2. From the equation, we could get the stoichiometry relationship, and we see that for every 2 moles of lithium, we get 1 mole of H2. Remember that this is the stoichiometric equality, which means we really could write 2 conversion factors. We could write 2 moles of lithium over 1 mole of H2, or we could write 1 mole of H2 over 2 moles of lithium. So remember, these are our 2 conversion factors that we could get from the balanced equation. And again, we're not going to use both of them. We're going to use whichever one's going to work in our case. So if we go back to starting with what was given to us, which was 5.32 moles of lithium, we want to get rid of lithium and end up over here at H2. So we need lithium to be on the bottom, so it's opposite. So we do need to use conversion factor here on the right to do that. And if we do that there, 2 moles of lithium on the bottom and 1 mole of H2 on the top. That is the big stoichiometry move. Comes from, again, the coefficients in our balanced equation. The moles of lithium will cancel. We're going to take 5.32 divided by 2. That's going to give us a 2.66 of hydrogen, which is right there. Now, in this particular case, that is actually what we're looking for. So we could box this thing if we wanted to. We actually do not need to do step number 4 in this case because we already calculated the moles of hydrogen. If I wanted to figure out, for example, the moles are the grams of hydrogen, I could do step number 4 and I would go moles to grams using the molar mass of H2. But in this particular problem, we don't need to do that. So we actually could stop here. And that does happen sometimes. Sometimes maybe you're just interested in moles. You don't need to go all the way to grams, but sometimes you do. And a lot of times you do. So in this case, we actually only had to do 3 of the 4 steps. Step number 1, balance the equation. Step number 2 was done for us. Step number 3 was our mole-to-mole relationship. So again, we're just going to go in order as we go through this. By the way, this is a product that was produced, and this is what is sometimes referred to as the theoretical yield. And a yield is a product, and the theoretical yield is pretty much the maximum amount of product that you can make based on the equation. This would be the theoretical yield in moles. if we did do that conversion to grams, we could figure out the theoretical yield there in grams. So hopefully you can kind of see a little pattern here. Just want to follow those 4 steps. All right, let's take a look at another one here. Now, using the same equation we just did there, we want to know how many grams of H2 would we form if we started with 81.75 grams of lithium. Some information in case you don't have a periodic table, lithium is 6.941, 1.008, I think. And I think that might be all you need. So take a few moments here and again, follow those 4 steps. Balance equation, convert to moles, relationship, and moles to some other unit. All right, so take a moment and see what you come up with on this particular one here. Okay, let's take a look here and see what you're doing. So again, we're going to follow our same 4 steps. We actually have step number 1 done for us, as it is the same equation that we were using previously. So then we could just move to step number 2. Do we need to do step number 2? The answer is yeah, we do, because we are given grams of lithium. And we ultimately want to find how many grams of this guy here. So because we're given grams, we do have to do that. That means we need the molar mass here from the periodic table of lithium. So step number 2 here is going to take our 81.75 grams of lithium. Using the molar mass from the periodic table, again, grams are going to go on the bottom there so that they cancel. 6.941 grams per mole of lithium. Grams will cancel. Again, you don't necessarily have to get an answer at this point, but if you did, try not to round too much. So if we did get an answer at this point, it's going to be something like 11.7778 moles of lithium. Once again, I'm going to take it to a few extra digits. I'm going to really just keep the whole number in my calculator as I go through this. But we now successfully have done step number 2. Now the next thing is the mole to mole relationship. So once again, we're going to go to the equation. We're going to find the 2 things we're interested in: lithium and hydrogen. It happens to be the same one that we just used on the previous problem. And once again, what we're looking to do here is go from lithium to hydrogen. So we need a way to do that. So we find from the equation, again, just the coefficients there, that for every 2 moles of lithium, we're going to get out 1 mole of hydrogen. Once again, that's going to give us the same conversion factors we used on the previous part of the problem. 2 moles of lithium over 1 mole of H2 are 1 mole of H2, 2 moles of lithium in this case. So we have moles of lithium. So I'm going to continue on here with my number. Lithium to go away and end up with hydrogen. So I am going to use conversion factor here on the right in this case. And that's going to put my lithium on the bottom. And 1 mole of H2. So this is the big stoichiometry step. That's going to get rid of my moles of L2 or Li, lithium, and divide it by 2. Going to get me something like 5.8889 moles of hydrogen. So again here, that is the 3rd step. I'm not going to round too much here because I actually do need to go 1 more step, because in this case we are looking for grams. So we do need to do the 4th step here. A reminder that at this point we have successfully converted from lithium to hydrogen, which means now when we want to convert that into moles to grams, we need the molar mass there of our H2. Molar mass of our H2 should be 2 times 1.008 grams per mole. That comes from the periodic table. And that's going to give us our 2.016 here. And we're going to again use that as a conversion factor. So 5.8889 moles of H2. Again, we want moles to cancel, so we can go on the bottom with moles of H2 is 2.016 grams. Moles are going to cancel, and that's going to get us 2.016. Looks like maybe 4.06 grams here of H2. So once again, you should hopefully be able to see that it is just the same 4 steps along the way. And here, sorry, I think I punched the wrong number in there. I think I did. Didn't feel right to me. Let's try that again. Maybe punch the right number in would be great as well. So let's try one more time here. Take 2, 5.8889. That would be a better number. Times 2.016. That is going to give me 11.87 grams of H2. That looks a little bit better there. Sorry about that. And again, in terms of significant figures, this is the only real number that we had, which was 4 significant figures. So at the end here, we do want to kind of clean it up to 4 significant figures and also put the right number in the calculator. I suppose that helps as well to get the right answer here, which is 11.87 grams. By the way, this is also a yield, as hydrogen is a product. This once again is what is referred to as the theoretical yield. And what this really says in this reaction is this, or this sort of problem is, if you did this reaction and you threw into this reaction 81.75 grams of lithium, and everything went perfect in the reaction, there was no side reactions, you weren't a klutz and dropped things on the floor or anything like that, you, in theory, which is why it's called a theoretical yield, should yield 11.87 grams of hydrogen gas out in this reaction. So that's what that number really means. Once again, here are a couple just things to think about as we're doing these problems. You should hopefully see the pattern. We have our first step, second step, third step, fourth step. In this case, we had to do them all together. Once again, you could do the calculation without getting a number or an answer in between and just kind of go 1 to 1 there. And that's perfectly fine as well. If you do get an answer in between, make sure that you do, again, take it to a few extra digits there. All right, so let's take a look at some more here. The other thing I did want to mention actually before we do that is the idea of what we were doing here, which is in 2 places, molar mass. Yeah, so we did the molar mass there. We did the molar mass there. We have an equation where we look at the equation, and once again here we see that has a coefficient of 2, that has a coefficient of 1. Remember that, as we talked about previously, when you're calculating molar mass that comes from the periodic table, in each of those cases, you do it based on just the formula. So you do not do it based off the coefficient, because that's really the stoichiometry, which is what we use here. So a super common mistake that people make is, as they go do the molar mass, they'll incorporate, for example, for the lithium, and times it by 2, and then do the 2 again, and you'll get the wrong answer. So really important, molar masses only based off of the formula. One of the formulas, regardless of the coefficient in the equation, that coefficient will be used in the stoichiometry part of the calculation. So don't use it in both places. So molar mass only based off of the formula. So I just want to again point that out. Again, a very common error that people make when they do these type of problems. All right, continuing on with our stoichiometry palooza here. Why don't we try this one here? A lot more letters and stuff, huh? 765 grams of C6H12O6 is consumed by the body. How much mass? So we'll be looking for how many grams here of CO2 will we produce? Let me give you some numbers here that might be helpful. Carbon, 12.01. hydrogen 1.008 from the periodic table, and oxygen 16 from the periodic table. Once again, follow those steps, even though it may look scarier here with some bigger things. We want a balanced equation. We want to convert to moles. We want mole to mole relationship. And we want moles to some other unit. All right, so take a moment or two, see what you come up with here. Again, follow those 4 steps, and hopefully she gets you to the right spot. Okay, let's take a look here. So we have an equation, and if you checked it, it is balanced here. So that's good. We are given pretty much 765 grams of this guy here. And we are looking in this case for how many grams of CO2. So this is definitely a stoichiometry problem. We got our balanced equation. Do we need to do step number 2, which is convert to moles? I hope you are shaking your head yes, because we are given grams. So we do need to do the second step. Reminder here, to do that, we will have to go to the periodic table there and figure out the molar mass here of our C6H12O6. So doing that there are 6 carbons, each at 12.01 from the periodic table. There are 12 hydrogens, each at 1.008 from the periodic table. And lastly, there are 6 oxygens, each at 16 from the periodic table. Doing all that together, that's looking like a $180.2 grams per mole. That's what we're going to use again as a conversion factor to convert our grams into moles. The reason we really need to do that again is that's the whole stoichiometry part. So the stoichiometry part is a mole to mole relationship, which means whatever they give us, we got to get it into moles. So that's why we're doing this. So we'll take what they gave us, which was 765 grams of C6H12O6. We will use the molar mass with grams on the bottom so that they cancel. 180.2 grams C6H12O6 per mole. C6H12O6. Grams are going to cancel in this case, and looks like here 765 divided by 180.2. Here's a 4.2453 moles of C6H12O6. So we did step number 2. The reason we're again doing that is to set us up to do the stoichiometry. Now we're ready to look at the stoichiometry. So once again, we're going to go to the balance equation. Remember, none of this works if it's not balanced. We're going to find what they gave us, and we're going to find what we're looking for. And that is where we're going to get our mole to mole relationship. And again, is nothing more than just the coefficients from the equation. And from the equation, we see that every 1 mole of C6H12O6, and again, that comes from the coefficient here, which is 1, gives us 6 moles of CO2. Once again, that's going to give us our 2 conversion factors that we could use. And if you want to write them out, you can. Maybe you don't necessarily have to, but if you did, it would look something like this. And again, that's coming from the balance equation where we're getting these relationships from. Now we're going to do the steps. We're going to take the number we just got, which was 4.2453 moles of C6H12O6. We're going to pick the conversion factor that's going to cancel that out. So we do need the C6H12O6 on the bottom. So we'll use the one on the right there. And that's going to give us 6 moles of CO2 up on top. And 1 mole of C6H12O6. That is the big stoichiometry move from the balance equation. That's going to take us from this guy over to this guy. And again, what stoichiometry is, it's finding the conversion factor to do that. And we're going to use the equation, the balance equation, as our conversion factor to do that. So that is going to cancel those out. I'm taking, again, the whole number is still in my calculator. I'm going to times it by 6. And that's looking like a 25.4 0.47, I'll call it 2 moles of CO2. That takes care of step number 3. If I wanted moles of CO2, frankly, I would be done at this point. I could be a box on it, but I don't want moles. I do want grams. So we do need to do step number 4, which is now convert our moles of CO2 to grams. And to do that, remember, we will need the molar mass here of CO2. So CO2, because we're no longer at the other guy, we convert it over to CO2. That would give us 12.01 for the carbon, plus 2 times 16 for the oxygen. It'll give us a 44.01 grams per mole. So lastly here, we're going to take our number that we didn't round too much with. And again, I have the whole number on my calculator, so I'm just going to continue on with the whole number. We're going to use the molar mass from the periodic table, again, done based only on the formula of CO2. Again, not the coefficient or anything like that. So we're going to go grams up on top, 44.01, moles on the bottom. And again, remember, as I've been talking about, molar mass is grams per 1 mole. So again, that's why we don't take the coefficient into account. We're going to times it by 44.01. That's going to give us a number of 1121 grams of CO2. Now, in terms of sig figs, this is the only number that was pretty much given to us. Everything else is multiplying and dividing here. So 3 significant figures there means we probably should end about there. So probably a little 1120 grams of CO2 would be the proper sig fig wise. Again, no decimal, otherwise that's 4, not 112 because that changes the value of the number. And once again, this is a product, so this would be our theoretical yield in this case. Again, hopefully you could see the pattern. It really is just those 4 steps. Just follow it step to step to step. Go forward if something's done for you. And this should be the pathway that will lead you to the right answer. Once again, here, we started with our balanced equation. We converted to moles, mole to mole relationship, and moles to some other unit. So again, those 4 steps just repeated. All right, so hopefully you're getting these numbers. So let's take a look maybe at another one here. So see what you come up with here. How many grams of cisplatin, whose molar mass is 300.1 grams per mole, can be obtained starting with 0.7752 grams of K2PtCl4, molar mass 415.1 grams per mole. So they're nice enough to give us the molar mass. These numbers would come from the periodic table, but we don't have to look them up in this case. So give it a go. Same 4 steps. Okay, let's take a look at it. So you may be going, it kind of looks scary. A lot of big formulas and stuff like that. But it really, again, is our same 4 steps. We're going to, again, balance the equation. We're going to convert the moles, basically get it to grams to moles if need be. We're going to do our mole to mole relationship. And then we're going to do our moles to some other unit. So looking at this equation, as scary as it may look, yeah, it actually is balanced. So we're good to go. That's maybe a relief. There's some coefficients there. Now, when we look at the problem here, we are given here, where it's at there, 0.7752 grams of this guy. And we are eventually looking for grams of this guy. So we're going to take our next step, which is we do need to convert to moles. So we're going to take what was given to us, 0.7752 grams. Once again, they were nice enough to give us the molar mass. If not, you would be going to the periodic table there and those bottom numbers. And again, adding up all the parts to get to that number. But in this case, they gave it to us, so we don't have to actually do that part and go to the periodic table, but that is where you would get it if you needed to. We're going to put the grams on the bottom here. I guess I should write what it is, K2PtCl4, and that's K2PtCl4. At this point, the grams are going to cancel. Now, in the previous examples, I did get an answer at this point, and in this case, I'm not. I'm just going to kind of do all the steps together. Once again, you could get an answer at this point, take it to a few digits, don't round too much, but I'm just going to kind of do it all in one step here. So this basically represents step 2 that we just did. Now we do need to do the mole-to-mole relationship, and again, we would go to the equation, and it is between this guy and this guy, and that doesn't look too bad. That looks like a 1-to-1 relationship. So if we do that, we see that for every 1 mole of our K2PtCl4, we get 1 mole of our PtNH3 2Cl2. So I'm going to do that for step number 3. Remember, setting it up here like dimensional analysis, which is how you should set it up. We could clearly see that moles of our K2PtCl4 is on top. So that means moles of that needs to go in the opposite location on the bottom, and that will allow it to cancel. And moles of what we're interested in will go up on top, which would be PtNH3 2Cl2. I'll try to squeeze it in there. The moles of this guy are going to cancel, and that's really step number 3. Once again, if you're doing this sort of step by step, you could get an answer. Don't round too much. But again, I'm going to just continue on instead of doing an answer here. And what I see now is I need to do step number 4, which is take our moles to grams. And at this point, we are still in a good shape because they did give us the molar mass here. Once again, if they didn't give us the molar mass for our product here, we would need to go to the periodic table and figure it out, but they gave it to us. So once again, using our dimensional analysis, we have moles of our product up on top. That means on the bottom needs to go moles, and up on top should go grams, which is 300.1 grams. The moles are going to cancel. That's going to leave us with grams of what we're looking at. And again, here, that would be step number 4. Remember, we're going to multiply whatever's on top and come back and divide by whatever's on the bottom all the way across. So essentially, in this case, we're going to take 0.7752. We're going to times it by 300.1. Remember to hit equals, and then we're going to divide it by 415.1. And that's going to get us 0.604 grams of our product here, cisplatin, PT, NH3, Cl2. So once again, same 4 steps, although it may look scarier. Balance the equation, convert the moles, mole-to-mole relationship, and convert moles to some other unit. These 4 steps all in a row. Once again, as you can see here, I just want to demonstrate just doing it all in one calculation. Perfectly fine. Do you need to set it up like this through dimensional analysis where you can see the units canceling, giving us our product? And this also is our product, so this is a yield. And once again, this is our theoretical yield in terms of our product. So in this case, if we put into this reaction 0.7752 grams of our reactant there, we should, if everything went perfect, get out 0.5604 grams of our product. Again, 4 steps. I don't have a preference, so if you like getting an answer after each step, absolutely do it that way. If you like just to kind of do it all in one calculation, do it that way. You do need to make sure you show the work with the units, dimensional analysis when you're doing it. In addition, if it helps you to write the equalities like I did on the bottom, you could do that. If it helps you to write the conversion factors like we did on some previous problems, you could do that as well. You don't necessarily have to do that for credit in terms of the class. What you do need to show really is at minimum, something like this part of the calculation here, all this here. On previous ones, minimally, you need to show, if I can find it here, you need to show just kind of these steps here, these kind of steps that we did. You don't necessarily, again, have to write out the individual conversion factors and stuff like that. So if it helps you to do so, go for it. But minimum, you got to show really the stoichiometry work, the units, the setup, and everything working and canceling out correctly. Again, a reminder, as we talked about, you could go from reactants to products in stoichiometry problems, go from products back to reactants. You could see on the reactant side of the arrow. So we could do some relationships between our reactants here. We could also do some relationships between our products as well. What do I mean by that? For example, again, if we figured out how many moles of this guy or grams of this guy, we could then figure out how much of this guy. And again, we could also go backwards as well. This way, we could go there to there. So we really can do a stoichiometry on any side of the arrow, crossing the arrow, same side of the arrow. Again, a reminder, sometimes people always think you have to cross the arrow one way or the other. All right, so these are basic stoichiometry problems. What is next is limiting reagents. Dun, dun, dun. No. All right, so actually, I think this is probably a pretty good stopping place. Otherwise, it's going to be really, really long, the second part. So we will stop here. We could call this just our basic stoichiometry problems where we follow these 4 steps. The good news is, as we'll talk about in the next one coming up, our limiting reagent type problems is still the same 4 steps, but a little extra stuff that you have to do along the way in those type of calculations. So for now, basic stoichiometry problems, part 1 of chapter 9. Part 2 coming up shortly. We will get into a little bit more complicated sort of calculations where we'll kind of build on what we did in this recording. So for now, thanks for watching. We'll see you in part 2 coming up, and have a good one. I'll talk to you in a bit. Hello, and I hope you've enjoyed this lecture. So it's time now to finish like we like to do here. What do you get when you combine uranium, fluorine, and oxygen? Perhaps you get a UFO.